Hello guys, today we're going to get familiarized with TIA portal Siemens. And I will start from the very basic. And the goal is just to familiarize you guys with how it works and what is the basic idea of it. Furthermore, I will be using FBD language, so that's the block language. And yeah, let's get started. So when you open up TIA Portal 15 for the first time, this is what you will be encountered with, and it will ask you to open an existing project or create a new project. Let's go ahead and create a new project, and over here we can name it. Let's say learning 2, because I think I already have one. And then here we can, here's the author's name and the version of the TIA portal we can use. And over here you can choose the path of where the file is going to be saved. And here you can have some comments, and let's say for YouTube, for example. And then we can go ahead and create it. And just like that, your project has been created and we can start programming, but not so fast. First, we have to configure a device. So if you're familiar with Siemens devices, the input and outputs, let's have a look. All right, so roughly this is what it looks like in a way. Well, here you got the power cord, of course, at the back, and then you got the CPU, and then the device right next to it. So this one would be, let's say, input, and over here you would have the output. And we are trying to configure something similar in this simulation. So this is basically a simulation of real life. So over here we go to configure a device, and let's go to add a new device. Then of course here you have all the possible ones, at least all the latest ones to this date are available on TIA Portal 15. So over here I'm going to just I'm not familiar with this one, but well, actually let's go with this. Doesn't matter. I'm just going to pick a very basic one. I'm going to pick this one because I worked with this before. This is the most basic one, really, but it is good enough for what we want to do. All right, so after you have chosen your CPU, then we should, you don't have to do this, but it's really good practice because in real life you do need this. We should choose the power cord. So over here in PM, let's go with this. Hopefully it will be compatible. Here we go. And then right next to it in the second row, we have to choose a DI, which is digital input. And let's just go with DI. Yeah, let's go with this, should be compatible. And then let's close so that you guys don't get confused. Then we go to DQ. And if you remember from the last video, Q was for output, so digital output. And let's choose something similar with 16, 0.5 amp. Let's choose a high frequency. Maybe this one should be pretty good. So let's have that for the output. And look at this. Maybe I can zoom in a bit. So look at this. It looks quite similar to the picture, kind of. All right. So after we're done with this, we should have a look at these. So over here at program blocks, we have main. If you have ever done any programming, for example, if you have ever used C or even Java, C++, you would know that the executable program has to go into main. It is no different over here. This is very much like programming. Anything you can do in program. Program is basically logic. You just write a bunch of logic, which you want to call code, and then it will execute. They will work together and they will execute a task for you. This is no different. This is no different. And over here, you can add a new block, but whatever block you want to be executed must be dropped into main. Let's see what I'm talking about. Let's add a new block. And the language that I'm using, so let's go with function, is FBD. So the options are LAD, STL, SCL. LAD is the most popular one, but FBD is the newest one and it's the best one. It's the most logical one. So I'm going to go with FBD because that's the only one I know actually, to an okay extent. So let's go with that. Okay. And there we go. Okay. So over here we have a block title and comment. So just like how you would go to see, for example, like this, you would write comment. Well, there is no need for the dashes here. You just go to the comment and you start writing whatever you want, and these won't interfere with your program in any way. They're just for you to remember. So if I write over here, maybe learning, perfect. All right, so right up here, let me drag one of these over here. So you see this is a block, and it has a symbol of an and because it's called an and gate. And up here you will see the most popular and used blocks, but really these are not the only blocks available. To my right over here, I don't know if we can zoom in more. Nope, I can't. But over here there are a lot more gates. Like for example, if I go ahead and maybe grab an RS gate. So as you can see, there's an RS gate, and that's a reset set, and we're not going to get into that. That's a little bit too advanced for now. But as you can see, there are many other ones, and these are just the basic blocks. So this is a very capable programming language or program. So yeah, and Siemens is usually used for in industrial programming, so PLC, program logic control. And over here you have extended instructions. For example, we could add, one of these. Yeah, these are more complex, and I don't even know what this does. So, it's quite big, the world of PLC. But let's learn the basics and let's go from there. So here is an AND gate, meaning that, for example, we say that if x equals 2 and let's say y equals, let's say 4, then I'm going to write the function if, let's say, if x equals, say, 2 and y equals, say, 4, then do something. Okay, so this is saying that if this and this is true, then do something. It will make sense in a second. So let's look at the next block. It's an OR gate. Now, what is that saying? How is that different from this? So similarly to this, if we have x equaling to 2 and y equaling to 4, now this one is saying that if x equals 2 or y equals 4. So this AND gate doesn't settle for anything less than both of the values equaling to their set value. But the OR gate is more flexible. It will settle for either one. So if x equals 2, then it will execute it. If x does not equal 2, but y equals 4, then it will execute it. But if neither values equal, their set value, then it won't execute anything. And over here to the left, you put the inputs, as we discussed what inputs are. So you just write your inputs, and to the right it gives the output, and the output gate is over here. It has an equal sign. So there we go. This is an output gate, and it's always connected to the right of a block. And to the output gate, of course, if you're making a very complex program, you can put another gate, for example, another AND gate, and then let's say, I don't know, then you would reverse, you have a reverse connection to it, and it can get quite complex. You can just make your own logic out of it. And that's why you need truth table most of the times for this. Okay, so the next one is actually not used that often. It's an empty gate, so it can be anything, whatever you desire it to be. So over here, you can choose it to be anything. So, you know, if you don't want to go look for them because there are so many, as you can see, if you know the name, then, you know, you can just alphabetically look for it. For example, this is a I identify, P identify gate. Wow, that's a complex one. Okay, let's get rid of it. All right. Over here, we have a connection. So, you know, this is originally meant to be an input. So, you know, you can put it over here. Well, of course, not over here because it's an input. And also, well, I'm adding more input branches now, but also you can press this yellow thing to get more inputs. So now we have what? 7 inputs. And similarly, you can just get rid of it by deleting them like this. Yep. It's a reverse. It's a not. And so what does that mean, not? It means that, for example, if I say that over here, again, through this code, say 2 plus 2 equals 5, and then I would have a not gate. Let's just write not over here and right next to it. Then this is true. You know, it's a Boolean value. It's like a true and false, and then this is true. Even though 2 plus 2 is not 5, it's false. Since I put a not next to it, then it's correct. Yeah, 2 plus 2 is not 5. So how would we use this? We would say, for example, if it just like an input, but then it will be reversed. So when an input is for example, when an input is 0, then with an OR gate it's a 1. With a NOT gate it's a 1. When it's a 1, then it's a 0. So it's just reverses whatever it is. And over here we have branching. So for example, if I would put it over here, then I can start connecting, you know, something else. So I can put this whole gate and connect that gate over there. Now it's an AND gate connected to 2 OR gates, and you just have to think about the logic. And then finally output. Okay, so I actually want to stop over here, and I want to do an example, because I feel like if I go further without explaining these basics, everybody will be very confused. So let's just, you know, start using the basics that we have already learned, that discussed, and let's just put them into use. Let's see how we can use them. So let's go back to the problem from the previous video that I had. Okay, so this is the problem we're going to try and solve. So basically, when input 1.0 is basically when one of the inputs, when the first input is 1, then the output, which flashes at 0.5, so a light that flashes at 0.5 hertz frequency turns on. When the second switch is on, then the second light, which flashes at a different frequency, happens to be 1 hertz, turns on. And then finally, there is another switch. And I know that these are all different inputs because look, they all have different locations on the memory. So this one is at 0, 0, this one is at 0, 2, and this one is at 0, 1. If at least 2 of them were the same input, then they would have the same number. So you would say 0.1 and then also input 0.1. So that's how you know that which input exactly you're talking about. Anyway, so the third input, which is 0.0, is some kind of a main switch. And so it says both outputs, both of the lights are in state 0, regardless of the state of first switch and the second switch. So when the main switch is on, neither of the lights may be on. Okay, so let's make this over here. All right, how would we make this? Okay, so before we start doing this, let's start implement this, the inputs and the outputs. And doing this, we have to go to the tag table. So here's a default tag table, and we can just use the default one. So let's say switch 1. So switch 1, data type is Boolean because it's 0 and 1. You know, it's either 0 or it's either 0 or it's 1. So it's like either true or false, on or off, same thing. And it's I. So over here, you know, we have I, Q, and M. Q is output, I is input, and M is memory. And we'll talk about memory in a second. We actually need to use memory, I believe. And address is 0, and bit, I believe it was 0.1. There we go. Then we have switch number 2. And it also happens to be a Boolean, and it's actually, it did it for us, 0.3, 0.2. And then we have main switch, and I think it's going to give us 0.3. We have to change it. There we go. Yeah. So it was 0.0. And that's how computer actually starts counting. It starts counting from 0. So we have 8 bits. And notice we can't actually go beyond 7. So if I had another switch, so let's call this test switch. I'll delete it in a second or whatever. Notice if I put 8, 9, see 9, it didn't work. If I put 8, nope, syntax error, because it can't go beyond 7. 7 is okay. All right, let's delete this tag because we don't need it. Similarly with that, we have our outputs, which is light 1, let's call it, or rather 0.5 hertz, much better. And then let's say a light 1 hertz, like that. And this is automatically putting it as input. We have to change it. It's very important that you change the type to Q, and the address actually was 1 and I believe 1.1 it was. And then similarly with this, it was Q1 and 1.2. So it's very good practice to match the point, like the last number of the output and the input. So output 1.2 is corresponding to switch to input 0.2. And if you're wondering where I'm getting all of these numbers from, it's, you know, it's from the exercise. The exercise specified these numbers for the inputs and the outputs. Okay. So now, okay, so before we start, I want to show you one other thing, which is actually a property, a really neat property within PLC. So if we go back to our device configuration, so within the PLC, it actually has a clock hertz count, or I'm not sure how you call it, but I'm going to show you. Probably you guys will understand. So if we go to system and clock memory to PLC, so over here, system memory bits and clock memory bits. So we need clock memory bits, and look at this. It's basically, it will blink something. It doesn't have to be a light, it can be anything. It will put it from the state 0 to 1 at these given frequencies. And of course you can I think you can modify it with different versions, but this specific CPU is giving these specific options. All right, so now that we have that enabled, we can go back to our tag table, and we can, as you can see over here, these are all over here. And notice that they are all given, not with Q, not with I, but memory with M. And let's start using them. So in order to make your first program, you will need to go to program blocks, and then we will go to block 1, to our block 1. So over here we have multiple networks. So we have 2 networks, and we could have more if you wish, but 2 is enough for now. So let's start building our program. So we have an AND gate. So the first AND gate, let's put the first switch. And as you start writing, this tag table will actually suggest you all the possible inputs that you have inputted. So here is switch number 1, and then we have, let's say, the main switch as well. Of course, the main switch has to be there. Okay, Then we will need to connect an output. This is just to see how it works. And over here, it will suggest again. I'm not sure what it was called. If you don't remember, you can always press on this, and it was called, we called it light 0.5 hertz. Perfect. Okay, so finally, we need to add our clock hertz memory into this. So we wanted to blink at 0.5 hertz frequency. Perfect. So before I simulate this, let's think about what I have done over here. So I'm saying that if switch number 1 is on and the main switch is also on, then our light has to blink at 0.5 hertz frequency. Obviously, this is not what we want. This is not what the question asks, but let's just simulate it and let's fix it after. Let's see if it works. All right, in order to simulate, you will have to first of all save your project. Then it is very important that we drop our program, our block into main. So let's click on main. And don't worry about if it says OB language, it will automatically change to block language and it will be able to read block language. But if it bothers you guys, you can always come over here and change it. So properties, FBD, okay. And now it's FBD. All right, perfect. So then we can save it again and then press compile, which is this. So now it's compiling the program, and then we can go to online, then simulate, and then start. And okay. So this little thing will open, but don't touch it yet because it's not done compiling the whole thing. So then we start going online. Then we load. And then load again. And finish. Now we're ready to do it. So you can press run, and then we can minimize this. So we can go back to our block. And in order to actually see the effects, we need to do a couple of things. So first off, we would need to press monitoring. So these little glasses over here, we need to press it. So now we can actually see the effect of the simulation over here. And as we can see, all of our inputs are false, and our memory is obviously doing what it's doing. It's flashing at 0.5 hertz frequency. So it goes true, false, true, false. And lastly, in order to control your inputs, we would need to go to watch and force table. And then we go to force table like this. And then similarly of how we added inputs to the tag table, we start adding our inputs over here as well. So we have the main switch. Then we have our switch number 1. And we also have switch number 2. Perfect. So we can minimize this so that we can actually see what's going on in the PLC. Like this. Okay. So right now I only have switch number 1. So let's activate. So let's force switch number 1 to 1. Yes. So nothing should happen over here because remember, it's an AND gate. All the conditions have to be satisfactory. So they both of the inputs have to be true in order for an AND gate to be satisfied and give an output. So we also have to turn on the main switch on. And as you can see over here, our light is actually flashing now at 0.5 hertz frequency. Okay, so that was a quick demonstration. Now let's actually build the program that was asked for us, that was asked of us in the question. Okay, so let's minimize the watch table. Let's stop the simulation and close it. Make sure you close it. Perfect. Then we can go offline. Okay. Then let's go to block and let's actually build it. Okay, so this program can actually be built in several different ways. I'm gonna do, uh, as many as I know. So this is the first way. What we need to do is that we need to connect the main switch in reverse, so that because when the main switch is 0, that's when our light can be on. So when our main switch is 0, we want the program to think that it's a 1. That's why we use the reverse gate. So we're gonna do the exact same thing with the second output. So we're gonna put another AND gate, and let's give it the proper memory, which was, I believe, 1 hertz. Let's come a bit lower. All right, then let's give it the main switch. And finally, we have the switch number 2. Okay, perfect. And then let's give it an output. And this would be light at 1 hertz. Great. Okay, everything looks set. So this is a very, very basic way of building it. It's not ideal, but yeah. Let's save the project, compile. Good. And then online, simulate, start. Okay. Then we can run it. Well, not yet. Okay, now we can run it. And then monitoring mode. Yes. Let's zoom out a little so that we can see both of them. And then let's go for the force table. All right. So now everything seems to be false. Very good. All right. Let's turn on switch number 1. So turning on switch number 1 has to make the light, the first light blink at 0.5 hertz frequency, notice. But notice the main switch is off. The main switch is actually false over here, we can see. And that's what we want. And that's okay because it is connected in reverse. Okay, and I noticed that I actually forgot to connect the second gate on reverse, which I did really quickly, and now we can resume. Okay, so let's turn on switch number 1. So the first light starts blinking, and then also let's turn on switch number 2. So the second light also starts blinking at different frequencies. So now they're both on, they're both functioning. Then let's turn on the main switch, and surprise, surprise, they both go off because the main switch is on, and that basically satisfies the problem given. Now let's build it in another way. Let's go to the second network and let's build it in a different fashion. So the second way I'm going to do this is going to be technically wrong, but realistically it will work. And also I'm doing it just so that we can have some extra practice and we can understand better. And also it's a good excuse to use the OR gate. Okay, so we're going to use the OR gate. OR gate is very flexible. We're going to turn on one single light at different frequencies. So in order to do that, we would need one absolute, which is main. Main must be off, that is for sure. But either switch number 1 or switch number 2 may be on, and that is what we're going to use the OR gate for. So I'm going to put an AND gate next to the, attach it to the OR gate. So on the first AND gate, I will write switch number 1. And that's not caps. And then I'll put the frequency, the memory bit. So let's say 0.5 hertz. frequency. Then over here, we're going to go with switch number 2. And we're going to put 1 hertz frequency. Nope, doesn't want to give it. All right. Okay, 1 hertz frequency. And that is all connected to an OR gate. And what we need to do then is we need to now make our absolute. So now we need an AND gate. And the AND gate must be true in order for this to work. So we're going to put the main switch over here. Oops. There we go. Main switch over here, and we're going to connect it in reverse. So that when it's 0, the program thinks it's 1. So that we can get our output. But the problem here is that we were specified 2 different outputs. But now, with this method, so since I have one single so-called, let's call this circuit, I can have 1 output. So several outputs, it's unorthodox in this. It's possible, but you know, it's more complex. Not this way, not with the way I'm doing it. It's not possible. But yeah, let's go ahead and put, you know, just 1 light. Let's say that let's put the 0.5 hertz frequency light, but let's imagine that this output, this single light, is able to flash at different frequencies. So let's say that we have actually, you know, with this circuit, we have modified the voltage in a way that the light is able to flash at 0.5 or 1 hertz frequency. Okay, let's see how this will work. Let's start simulating it. So let's save it and let's go online. Simulate. Okay, and let's run. And monitor. Zoom out. Okay, and let's have a look. Let's turn on the 1 hertz frequency switch. Okay, so as you can see, maybe like this. Okay, so as you can see, only the first branch. So since switch number 1 is on, then the first branch is able to make the light flash at 0.5 hertz frequency. And if we turn off this light and we go ahead and turn on the second switch, we can see that the light is able to flash at the 1 hertz frequency. But if you have been paying attention, by now you have picked up a very big flaw in my design. So what if we want to turn both of them on at the same time? Well, let's try it. Let's turn on switch number 1 as well. Okay, well, now they are both, you know, one is flashing the light at 0.5 hertz frequency, the other one is doing it at 1 hertz frequency. Ideally, we would want, well, ideally, with the question, we would want 2 lights, 2 separate outputs, and they would be flashing at different hertz frequencies. And also one other problem with this design is that I haven't restricted the switches. So if I were to design this better, I would make it so that if switch number 1 is on, switch number 2 cannot be on. Rather, if it is on, it wouldn't have any effect until switch number 1 goes off. And similarly, when switch number 2 is on, switch number 1 wouldn't have any effect. But I just wanted to show you the OR gate. Hopefully you got the idea. So I would, you know, I would go with this one, the first one. And we will do some more complex examples. Thank you.